We'll be looking at subtraction using nines complement, and this video will have multiple parts to it. First, I'll do an example with an explanation, then some additional examples including special cases, then I'll give you a little bit of a shortcut, and if you want to go deeper, you can continue on to why would you use this and how does it work? Why does it work? So our first example is 703 minus 647. In order to do this subtraction using nines complement, we recopy the number on the top, which is 703. We change subtraction to addition, and then we're also going to need to change the second number in the subtraction problem. And the way we change this does have to do with 9. We're going to look at each digit and say, what is 9 minus that digit? So 9 minus 6 is 3. 9 minus 4 is 5. 9 minus 7 is 2. And that's my new number. That's the nines complement. I'm going to mention another way to get that number, just for you to keep in for reference later. We could think of it as many nines as you have digits here, and then subtract that second number that we want to change. So you can see you're just doing 9 minus each number, right? Which is exactly what we did. But this might be a helpful reference for later. So continuing with our work, we're going to add. 3 plus 2 is 5, 0 plus 5 is 5, 7 plus 3 is 10. Now, obviously, that's not the answer to the subtraction problem. Something in the 700s minus something in the 600s does not give you something in the thousands. The final step is to take the 1 in the front and to place it at the back. And what I mean by place is to add the 1 to the number that's in the 1's place. So the final result here is 56. That's the answer to the problem. So let's check this. Let's go back and do the subtraction in the way, the standard method that people typically use. We look at the problem and we say, well, we can't take 7 away from 3 because 7 is bigger. So we want to look next door to borrow, but we can't borrow from 0. So we're going to come all the way over to the 7, borrow from the 7, bring that into the 10's place, continue with the borrowing. That's going to be a 9. And then we put a 1 in front of the 3, which gives us a 13. So 13 minus 7 is 6, 9 minus 4 is 5, and the 6 minus 6 is the 0 that we had here, but we don't write a leading 0. So the answer is 56, and that is how you do it. I'm going to do a few more examples. This one involved 3-digit numbers, a 3-digit subtracted from a 3-digit. So let's take a look and see if this works. If you're working with 4-digit numbers, 2-digit numbers, and after that, I'm even going to look at, well, some other instances, but even just 1-digit numbers, single-digit numbers. Okay, so the process is we keep the number on the top of the subtraction problem. We change subtraction to addition. And then for each of the digits down here, we're going to say what is 9 minus that digit. So for the first one, 9 minus 2 gives us 7. Then 9 minus 1 is 8. 9 minus 7 is 2. And 9 minus 8 is 1. Then we go ahead and add. 5 plus 1 is 6. 1 plus 2 is 3. 3 plus 8 is 11. So we are going to have to carry. This gives us a 17. Again, we see that the answer is obviously far too big to be the answer for the original problem. We grab the digit in the front, the 1. We add that to the digit on the back, the 6. And our final answer is 7,137. I want to make sure and add that 1. So at this point, if you want to check and make sure these are working out, instead of us going back and reworking all of them, just grab a calculator, grab your phone, open up the calculator, check it out. So 4 digits, let's go with 2 digits, same process. keep the number on the top, change to addition, and then find the 9's complement of the number on the bottom. 9 minus 1 is 8, 9 minus 5 is 4. Add, oops, that just wants to slide away there. 1 plus 4 is 5, 6 plus 8 is 14. Add the 1 to the 5 at the back, and we get 46. So the answer to 61 minus 15 is 46. So far, all of the answers, or all of the problems that I've worked, have had the same number of digits in both of the numbers in the subtraction problem. 4 digits minus 4 digits, 2 digits minus 2 digits. What do you do if you have a different amount of digits in what you're subtracting? Well, what you want to do is think of these empty spaces in the front as being zeros. So in order to do this first subtraction item, again, keep the number on the top as is, 1072, change to addition, and then find the 9's complement. So in this case, we're going to get a number that starts with 9, 9, because 9 minus 0 is 9. 9 minus 8 is 1. 9 minus 6 is 3. Then you do the addition, take the number on the front, add it to the number on the back. We've got a 5, then an 8, then a 9, then a 10. We take this, put it on the back, and the answer is 986. Of course, at any point, you could pause this and try one on your own to see if you've got the idea. So here, again, I'm going to augment the number with fewer digits by placing a 0 in the front. Recopy the number on top. Change to addition, and write the 9's complement. And go ahead and add. The number on the front, add it to the number in the back. And the answer here is 4,867. We can even do this if we've only got single digits. It's a lot more work to go through and make this change. We can just look at that and say, I know the answer is 5. But let's check it and let's see if it works. Keep the number on the top, change to addition. Turn the second number into its 9's complement, which is going to be 6, because 9 minus 3 is 6. Add. 8 plus 6 is 14. Take the number on the front, add it to the number on the back, and you get 1 plus 4, which is 5. That number on the front has dropped away. We have added it to the number on the back. And sure enough, 8 minus 3 is, in fact, 5. So this works even for single digits. So I want to give you a little bit of a shortcut. It's not a huge one. It really is just a little shortcut. But typically when I'm doing this, I realize that every single time I work this, I'm adding a 1 to the number on the back. And it's never going to be anything other than a 1. Because whenever you're adding 2 digits, no matter how big those digits are, and even if you're carrying a 1, you're never going to get all the way up to 20. You're never going to have a 2 to add on to the back. So I just go ahead and add that 1 right away and leave it off of the front. So that's going to be one bit of my shortcut. And the other thing I do is that when I'm coming up with the 9's complement for the second number, which I'm about to do, I don't really go through and say 9 minus 3 is 6, 9 minus 9 is 0. I look at the numbers and I actually think in terms of addition. What would I have to add to 3 to get 9? What do I have to add to 9 to get 9? It may be a small thing, but it just seems easier to me to think in terms of adding instead of in terms of subtracting. So here too, we're going to do the addition. 0 plus 0 is 0, but I'm going to go ahead and add the 1 immediately, because I know that's going to happen at the end anyway. Now I'm all the way to the left. 5 plus 6 is 11. I'm going to bring down the 1 but not the tens place there. I'm kind of playing fast and loose with place value, but hopefully you get the idea. And I've put another example next to that so I can do that again in case that went a little fast. Copy the top number, grab your nines complement. Now, 1 plus 3 is 4, but I'm going to write a 5 because I know at the end I'm going to add a 1 to it anyway. This would be an 11. I already took care of that one that would have been way out in front. So 321 minus 196 is 125. Okay. So why would anybody want to do this? Before I get, really, I have basically three things I want to share with this regard. So we're going to go back to a problem we already did, which is 61 minus 15. And we will look first at the method that is typically taught, has been taught for about 80 years in the United States. And that has to do with regrouping by borrowing. So the way we do that is we look at the problem, we say, oh, 5 is bigger than 1. I can't take a 5 away from a 1. So I look to the left and I borrow. So I take 1 from the tens place, I put 10 in the ones place, and then I go ahead and do the subtraction. I can do 11 minus 5, which is 6, and 5 minus 1, and that gives me 46, which is the answer we found earlier. This method was developed in the 1940s, and it's called the Brownell Method, after the person who developed it, and it was picked up pretty soon after in textbooks. And this is the way it's typically been taught in the United States for approximately the last 80 years. I'm going to show you another method. Here too, we're going to look at the 5 and the 1 and say, I can't take 5 away from 1, so I want to turn this into an 11. But rather than borrowing from the 6, I'm going to go to the number down on the bottom, and I'm going to increase the tens place by, well, another 10, turning the 1 into a 2. Then we'll go ahead and do the subtraction. 11 minus 5 is 6. 6 minus 2 is 4. I got the same answer. This method is known as equal addends because the process behind this method is to add the same amount to the number on top as you do to the number on the bottom. So I added a 10 to the 61, and I added a 10 to the 15 by making the 1 a 2 in the tens place. So that's equal addends. Now, as we do these subtraction problems, we keep saying, I can't take the 5 away from the 1. Well, once upon a time, a student said to me, what do you mean you can't take 5 away from 1? 1 minus 5 is negative 4. They said, can't you do subtraction like this? 1 minus 5 is negative 4. 60 minus 10 is 50. Put those results together, negative 4 and 50, and you get 46. Yes, absolutely that works. And then, of course, we have the method that we've been talking about, which is to keep the number up top. Oops. Add the nines complement. In this case, we get 145. I didn't use my little shortcut there, but we still get a 46. So what we're talking about here is, why would anyone use this method? Why would anyone use this method? Well, there are lots of different ways of carrying out subtraction. So the thing is, most of us, if we grew up in the US within the last 80 years, we're taught this method over on the left. And when we see that, we think that is subtraction. But what that is actually one method for doing subtraction. So I've presented 4 methods here, and there are other methods as well. So the thing is, there's lots of methods to choose from. And I've decided just recently to start using the nines complement all the time, because I've started working with old calculating devices, and I'm trying to stay true to the process. So I'm doing my calculations by hand alongside those calculating devices. And I end up doing a lot of subtraction. And I mean a lot of subtraction. And regrouping by carrying multiple times in every subtraction problem was giving me a headache. So I shifted over to the nines complement method so that everything was simply addition. Another reason why nines complement is a nice method is that with early calculating devices that used gears, if you wanted to subtract, you would have to run the gears backwards. But if you use the nines complement, where you are adding instead of subtracting, you can continue just moving the gears forward instead of moving the gears backward. And even to this day, when we have computers, cell phones, calculators, and things are digital, um, many, if not most of them, are still programmed to use the nines complement method rather than using like a regrouping by borrowing method. So those are just a few reasons why nines complement is used. So now we're going to get into how and why does this work. So this is going deeper than what we've done so far. And I'm going to go ahead and use the single digit example first. Let's run through that again quickly. We get 8 plus 6. And so I'm going to take it one piece at a time. This is 8, which is our original number. But then where did the 6 come from? So we're adding. And I'm going to break it all the way down. Like the 6 came from 9 minus 3. So right now, this is 8 plus 6. It's this thing right here. But then what do? 8 plus 6 is 14. I grab the 1 and I add it to the 4, which gives me a 5 as my answer. Well, what really happened there? Hold on a second. Well, the 4 got a 1 added to it, but we took this 1 away, and that 1 is actually in the tens place. So we actually subtracted off a 10. Well, if we simplify this a bit, 1 minus 10 is negative 9. I don't really need these parentheses up front. So we've got 8 plus 9 minus 3 minus 9. So I've got a plus 9 and a minus 9, which cancels out, leaving me with 8 minus 3, which is our original problem. And we know that 8 minus 3 does, in fact, have a value of 5, which is what we got. Now, that was a little bit involved if you're not used to thinking that way. So I'm going to do another example. So again, just kind of doing it step by step here. We keep the first number in the subtraction problem. So let's do that. Let's just start out with that. We keep it. Instead of subtracting, we add. Okay. But what do we add? We add the nines complement, and this is going to be 8, 4. Well, where did that 8, 4 come from? Technically, what I did was 99 minus 15. I mentioned that earlier. I said we could use that for reference later. It's a 9 minus a 1 and a 9 minus the 5. That's where the 84 came from. So what's down here is equal to what's right here. And then we go ahead and do the addition. So I get a 5 here and a 14 here. We take the 1, remove it, and add it to the back. So the answer we get is 46. Okay, so what's all that? What's all that? So what happened is that we added a 1 to this 5 to make it a 6. But now I didn't subtract off a 10, I subtracted off a 100. Has to do with place value. notice 1 minus 100 is 99. And maybe you can kind of look ahead here and see what's coming. But if I write out the rest of it, again, the parentheses aren't strictly necessary here. I just put them in order to sort of separate it and clarify what I was doing. So I have a minus 99 back here, a plus 99 up here. They cancel. And what that leaves me with is a 61 minus 15. And the value of 61 minus 15 is indeed 46. Okay. So I'm going to go ahead and do this more abstractly to show that it works for any size number. But what you'll need to notice is, first of all, we've got a 100 here and a 99 here. The difference between those numbers is 1. We've got a 10 here and a 9 here. The difference between those numbers is 1. Also think about the digits. In this first problem, I was working with single digits and we had a 9. We had a 9. Here we were working with double digits and we had a 99. If you look at the number at the very back that I have highlighted, again, for this second problem over here, we were working with double digits. I've got 2 zeros. I've got a 100, which is the same thing as 10 squared. Here, in this first problem, we're working with single digits. We have 1 0, and that is 10 to the first power. If I was working with a 3-digit number minus a 3-digit number, then at the back I would have a 1000, and in here I would have a 999. Okay, so hold that in your mind. Also, in order to make this really apply to every number, you could imagine we're going to do a little bit of algebra. So in a subtraction problem, the first number, the number on top, is called the minuend. The second number is called the subtrahend. And the answer to a subtraction problem is known as the difference. So I'm going to rewrite this as m minus s, minuend minus subtrahend, equals the difference. And then I'm going to talk us through what we did in order to get that in general. So we keep the number on top, the minuend. Then we turn subtraction to addition. And my computer seems to be going crazy with the pen here. We add the 9's complement. And so what we've been doing so far is basically 999 minus something, 99 minus something, 9 minus something. But to do that in general, what you've actually got is a power of 10 minus 1. Like 1,000 minus 1 would be 999. 100 minus 1 is 99. It's 1 less than a power of 10. So these are your 9s here. And then from those 9s, we subtracted off the subtrahend, the second number in the subtraction problem. Once we did that, what we did is we added 1 to the digit at the back, and we subtracted the number off of the front, which is going to be a 1 in whatever place you have out there. If you're in the 10,000s place, the thousands place, the hundreds place, you're going to subtract that off. So breaking this down, this is your top number, your minuend, plus a power of 10 minus 1, minus the second number in your subtraction, which is the subtrahend, plus 1, minus a power of 10. And once again, we notice that I have plus something and minus that same thing, so we get cancellation happening. And again, here I have plus something and minus that same thing, so we get cancellation happening again. And what's left, once we do that, is m minus s, the value of which is the answer to your problem. It's your difference. So basically, nine's complement is a way of adding something in and subtracting it back out, but it's kind of hidden. So let's just wrap up with one more problem really quickly. Let's do 617 minus 458. Write the number on the top. Change to addition. Write the nine's complement. Do the addition. And I'm going to go ahead and stick the 1 on the back right away. So 7 plus 1 is 8, but I'm going to make it a 9. 1 plus 4 is 5. 6 plus 5, boy, I keep getting 11s. But I'm just going to keep one of the ones because I already added the other one. So there's the answer. Once you've done this a little bit, it actually goes pretty quickly. If you stuck with me this far, good for you. I hope you enjoyed it, and I hope this gives you a nice alternative to the standard subtraction.